Greetings, this is Dr. Gross. Welcome to another installment of Easy SPSS. And today we'll be um, taking you through a two-way ANOVA, though this time with an expanded data set. So there will be a little bit more variable creation and data entry. So let's go ahead and open up your SPSS on your desktop. And real quick, we'll talk about why we use the two-way. Uh, we're interested in understanding how two independent variables, two categorical independent variables can influence one continuous dependent variable, both as individual factors and if they influence the dependent variable uniquely in some way together. And upon opening SPSS, you can see our two different views that we work in, data view and variable view. Data view is where we input the data. Rows are cases and columns are the variables. And variable view is where we define the properties of the variables, like their names and their measures. And so going back to that real quick, you can see here is our data view, kind of like a spreadsheet. And here's variable view, where we would input our variables. Now, we have previously created a data set, so I'm going to go to my open file folder, and we began with this data set. So I'll go ahead and open that up. And I can see in my data view that we have 12 participants, each row representing a participant, and 6 variables, each column representing a variable. And when I go to variable view, I can see those 6 variables, the name of them, the type, their labels, any values that we've input. Now, these are our codes, and we coded gender, 1 for male, 2 for female. We've coded diet type, 1 for low calorie, 2 for balanced, and 3 for high calorie. And today we'll add a 7th variable. We'll also code that categorical variable. The next important thing I should mention is the measure. Any categorical variable we would set to nominal. Any continuous variable we would set to scale. So we, in the last video, performed a one-way ANOVA. And when is the appropriate time to use an ANOVA? Anytime you're trying to detect significant differences in the means of a continuous dependent variable across 2 or more independent groups, and preferably it's more, preferably it's 3 independent groups, because if there's only 2 groups, then a t-test is sufficient. So the ANOVA is preferable for 3 or more groups to avoid really inflating the risk of a type 1 error without going into further detail. So just real quick, one way versus two way. One way, we're testing the effect of technically we had 1 independent variable, diet type, but we had 3 levels, right? So 3 categories: low, moderate, and high. And we were trying to see if those 3 categories affected our dependent variable. So again, even if there's only 1 independent variable, it can have multiple levels. And that's what we did in the last video, which made the ANOVA an appropriate test in that case. The two-way is now we actually have 2 separate independent variables. We're going to have diet type, which we already have input, and we're going to have exercise level, our new variable that we'll add today. And we're going to test their effects on a dependent variable. In this case, today, we'll test if diet type and exercise level have an effect on weight. Now, in a two-way ANOVA, the output is a little bit different. You'll have main effects, and these show how each independent variable, diet type and exercise, how they affect the dependent variable weight by itself. All right, so how does diet type affect weight? How does exercise level affect weight independently? The interaction effect will show whether the combination of those created a unique effect on a dependent variable. So, maybe an example. For diet type, we coded as follows. And we'll add exercise level and we'll code it as follows. And then weight is our dependent variable. And so this test will differ from a one-way, which only examined one independent variable at a time. So diet type on weight. Now in a two-way, we'll be able to see how both of these might affect weight independently and together. Do they have an effect on weight? So let's set this up in SPSS. We need to add our new variable. So now we already have it open. We'll navigate to variable view, and then we'll add a new variable called exercise level. So let's do that. And let me see if I can just side by side us. Sure, that'll work out, I suppose. So I'm in variable view right now, and I'll go to my next open row, number 7, and I'm off a bit. Let me go over to name. I will name this new variable, and we'll call it exercise level. And the default type is numeric, so we'll just leave that alone. We'll set the decimals to 1 to match. For our label, we can say, again, high, moderate, and low levels of exercise. Long label. Now, we do want to add some value labels, right? We want to tell SPSS what numerical code will indicate these categories. So we have 3 levels. So I'm going to hit the plus sign 3 times. And our values are 1, 2, and 3. And those represent low, moderate, and high levels of exercise. So we'll add that in. Low, moderate, and high. Okay. Now, these are categories. Right? You might fit into a high exercise category or a low exercise category, depending on your level of physical activity. So since these are categories, the measure is a nominal scale of measurement because it is categorical. Next step is to enter our data set. I apologize in advance. Switch to data view. I can do that right here. And when I've switched to data view, I can see that it's added in my new variable. So now that we're in data view, let's go ahead and enter this data set exactly as it's presented on screen. Now, you should have already entered participants 1 through 12. So we should just be entering new data for participants 13 through 32. And I will leave this on screen so that you can pause and enter the data. But I'll do participant number 13 with you real quick. So again, let me side by side this and participant 13. So I'll go down here. I'm in data view and I'm ready to enter some participant data. So I'll go over to 13 and this is the ID. So this is participant number 13. That's their ID. And the gender coded as 1. Move over to height is 68. Weight at 160. Age is 30. Diet type is 3. And then exercise level, our new one, is a 1. And I realize now that you won't have this data, so I will show you that data in a second. But go ahead and pause here. Excuse my error. Pause here and let's enter 13 through 32, those participants, their gender, height, weight, age, diet type, and exercise level. Go ahead and pause now and go ahead and enter that now. Okay, so you should have now this or these new data entered. And here is the exercise levels for participants 1 through 12. So you can go ahead and pause here if you need to and enter these exercise level values for participants 1 through 12. And as we did before with our one-way ANOVA, we need to check some assumptions before running the analysis. So our first assumption that we need to check is normality. So we'll go to Analyze, Descriptives, and Explore. And let me see if I can side by side this again. That might be easier for us to see. So we'll go to Analyze, Descriptives, and Explore. Analyze, Descriptives, Explore. And when the dialog box opens, we're going to place weight in the dependent list. And we're going to put diet type and exercise in the factor list. Under plots, we're going to select normality plots with tests. Here's normality plots with tests. I changed stem and leaf to histogram. That's preference for me. And we'll click OK. Now, here's the interpretation. All right, we're looking for the Shapiro-Wilk test in the output. If the p-value is greater than 0.05, the test is normally, or the data, excuse me, is normally distributed. And so we're looking for non-significance, and that would indicate that our data is normally distributed. And so here's our output. And as I scroll, I can see the descriptives for the data. And this is what I'm looking for, the test for, or the test of normality. So this is for weight and calorie intake, that variable. And when I look for the Shapiro-Wilkes test statistic, that's tough to say, I can see that the p-value, the significance, is well above 0.05. So we have maintained our assumption of normality, at least for that variable, the calorie or diet type. I'll scroll further and I'll see descriptives for exercise amount. And right below that, I'll see the test of normality for that variable. And again, the p-value is well above 0.05. So we do not have a significant Shapiro-Wilk test, which means that we have normally distributed data. And we're safe to move on as we have satisfied the assumption of normality. Next assumption to meet is the homogeneity of variance. And so for this, we'll actually have to run the model. So we'll have to run the two-way ANOVA. When we do, we'll place weight in the dependent field and diet type and exercise into the fixed factors field. And then we'll click options and then the homogeneity test. And that's how we'll check the homogeneity of variance assumption. So we'll revisit that in the output when we run the model. And what are we looking for? We're looking for Levene's test this time. And again, a p-value greater than 0.05 indicates equal variances across groups, which means that we have satisfied that assumption and we do have homogeneity of variance. So let's run the test. So I have my new expanded data set. And we're going to go to follow along, analyze general linear model univariate. So that goes away. Thank you. Analyze general linear univariate. Now we'll place weight in the dependent field. And we'll place diet type and exercise into the fixed factors. First, we'll click on plots. And when the dialog box opens, we're going to move diet type to the horizontal. And we'll move exercise level to separate lines. And I realize now I misspelled level. We'll click add. And then continue. Now, if the model is significant, we'll want to run some post hoc tests to see exactly where those significant differences are. So we'll click post hoc, and we're going to move diet type and exercise level over to this post hoc test. We'd like to test for both of those. We'll click on Tukey and Bonferroni as our tests. And then we'll click continue. Now, I mentioned we'll revisit this. We'll click options now. And I'm going to go up here to homogeneity tests so we can see if we've satisfied that assumption. We'll click continue. And we are now ready to run the analysis. So we'll click OK to run the analysis. So let's look at our results and how do we interpret them. So if we look at first Levene's test, so that we can see if we've satisfied that assumption. Levene's test for homogeneity of variance is not significant for any basis. So we can say that, again, we have satisfied the assumption of homogeneity of variance. So again, we're safe to move on. Moving on, I have our next output box of importance, the test of between subject effects. Now, the corrected model is the model significance. The overall model, we can see with an F value of 26.698 and a significance of P less than 0.001. So the overall model is significant. And what that means is that the combination of these factors, diet type and exercise level, strongly impacts weight. Right, that's a very significant level, less than 0.05 for sure, but less than 0.001, very significant. Now, we can also look at the R squared value to see if the model is a good fit. And we have an R squared of 0.874. Now, that interprets as explaining 87.4% of the variance in weight. Now, that is a very strong model fit. So what this is saying is that diet type and exercise level can account for 87.4% of the differences in people's weight. So very strong fit. However, when we look at the main effects, and our main effect is diet type and exercise level, those are our independent variables that we're trying to interpret and analyze. So we'll look at our main effects right here. Overall model significance, we looked at the corrected model, and that's where we saw 0.001. Now, our main effects are our independent variables, so diet type and exercise level. Diet type, if we go over 0.276, so not less than 0.05, so not significant. And exercise level, 0.054, not less than 0.5, not equal to it either. So technically not significant, though very, very close. And finally, we have the interaction effect right here, diet type, and then that asterisk exercise level. So do these two together have a unique effect on weight that is different than the effect of these two alone? And we find that no, they don't. 0.394 is not less than 0.05, so not significant. So the main effects are not significant, and the interaction effect is not significant, but the overall model is significant and accounts for 87% of the variance. So something's going on. So I think that warrants post hoc tests, which will tell us a bit more about about these differences, right? So our post hoc tests, they revealed significant differences between low and high exercise level, and we can see that in the multiple comparisons. So high balance, low caloric, Tukey's and Bonferroni are showing significant differences in the mean difference. We can see that level of significance right here, less than 0.05, less than 0.001. So all of them are significant, it appears. So significantly different between low and balanced, significantly different between low and high, and between balanced and low. Moving down, I can see now the exercise amount and the multiple comparisons there, and I am seeing significant differences among all groups. So low to moderate, low to high. So how would we conclude this? It is kind of an interesting conclusion. So the two-way ANOVA, a very strong model fit, 87.4% of the variance explained. Exercise level showed meaningful trends with low and high exercise levels differing significantly. Our interaction plot, it confirms the trend. And so you can see that exercise amount, this low exercise amount, is correlated highly with with differences in weight compared to these different categories or groups. You don't see a lot of interactions or lines crossing. You don't see that occurring very much at all, only in this one instance. And so that would again further indicate that the combined effects of these variables do not significantly impact weight. Now, since this was such a unique case, here's how I'd write this up. And we needed to expand the data set because that improves our statistical power, our ability to detect significant differences. And 30 is generally considered the number that you should have to have enough statistical power to be able to see these differences or detect them. But I imagine if we had a much larger data set, let's say thousands, that we would find that data and that exercise level and diet category or type, so to speak, do play a role in weight and weight management. But how would I write this up? So I'll read it to you real quick. But this would be a formal write-up. So in a dissertation or in an academic journal, if we had written an article, a two-way analysis of variance was conducted to examine the effects of diet type and exercise level on weight. The data set included 32 participants, and all assumptions for the analysis were met. The overall model was significant. I'm citing the F value right there with the degrees of freedom in parentheses, an F value of 26.698, the P value less than 0.001. These should be italicized, all right? In any statistical symbol should be italicized. I didn't do that, but you should when writing it up. Indicating that the combination of diet type, exercise level, and their interaction explained a substantial proportion of the variance in weight. The model's value, or the model's R-squared value, was 0.874, suggesting that 87.4% of the variability in weight could be accounted for by these factors. I go on to explain that the main effect was not significant, citing the F value and the P value. Again, citing the main effect of exercise level, the F value and the P value. However, I mentioned that this is very close and suggests a trend, which is the reason why I went into a post hoc analysis using the tests that I used, detecting significant differences. And when I do that, I cited the mean values and the standard deviations for those groups. And then I discussed the interaction effect, how it was not significant. Finally, I ended with the interaction plot confirming those findings. I go into a discussion of if I'm trying to support my claim, I can discuss that the overall model was significant, and that it explained a significant portion of the variance. And so I can use that definitely to support an argument or a claim. However, I did discuss, as you should, the non-significance and what that might mean, and reasons for that. And so I won't read all that to you. You can read, and it would only extend the video further. But you could definitely pause and read through that if you'd like. I didn't want to continue, but I would end it with, future studies could expand on this or improve upon this study by doing these different things. Or I might discuss how increasing my sample size and or the variability within my sample size, um, how that could improve my findings or future studies findings. So, thanks for tuning in. I'm sorry this one was a little longer, but we needed to expand the data set as we move into these more advanced statistical tests. So tune in next time as we dig deeper into statistical tests on SPSS. SPSS. Thank you again, and good night.